is Peter Haffinger. I'm a co-founder of Delft Inversion, and the title of my E-Lecture is Quantitative Prediction of Injected CO2 at Sleipner using wave equation-based AVO. So this is what I have on the agenda today. You see, this is the Sleipner gas field in the CCS project. We will give a high-level introduction to wave equation-based AVO. We will discuss the impact of multiples and mode conversions. And then we'll look at the inversion results and how we quantitatively predict the amount of CO2 in the subsurface. And at the very end, we will end up with a couple of conclusions. This is the Sleipner site. Equinor, they produced gas from a 3-kilometer deep gas field for a long time. But then what happens is once the gas reaches the platform, they realize that they could produce up to 9% of CO2 with it. And it turns out that the best way to go about it is to re-inject the CO2 into the subsurface. This re-injection happens into a much shallower formation. It's a so-called U0 formation. It's approximately 1 kilometer deep, and the formation can be characterized by very high porosities. So the porosities are on average 35%. They go up to 40% even. And you can imagine that when you inject a low density CO2, that then you will create a highly scattering seismic environment. And that is where the wave equation and web AVO comes in handy to do a proper quantitative characterization of the subsurface. Location-wise, we are halfway between the United Kingdom and Norway. A couple of facts on the Sleipner project. It was in 1996 when the first CO2 was injected into the U0 formation. By now, it is the longest running industrial scale aquifer CO2 storage project. Between 1996 and 2014, a total of 8 time-lapse surveys have been acquired, and in the work that I showed today, we will use the dataset from 2008. And by now, more than 150 papers were published about Sleipner CO2 and its associated monitoring. So Sleipner is a very prominent site to demonstrate new technologies and new methods. This is just a demonstration of the seismic data. You see here an inline and a crossline, and you can see that the seismic amplitudes, they respond strongly to the injected CO2. You can also nicely see the top of the storage formation. You can nicely see the base of the storage formation, but you also clearly see where the CO2 is present or where it is accumulated after the injection. The situation becomes even more clear when you look at the time slice, and I think it's very clear that the pure delineation of the CO2 plume is rather straightforward based on the seismic amplitudes alone. But again, in this work, we're not interested in the delineation, but we will be interested in getting a quantitative estimate of the CO2. So on this slide, you can see the effect of CO2 on the seismic. On the very left, you see the first data set from 1994. So this data set was acquired before the first CO2 has been injected. And you see that there are no strong amplitudes visible on the seismic. But then you can also observe that when you progress in time over 2001, 2004 to 2006, that then with increased injection, the amplitudes on the seismic get stronger. And if you look at the time slices below, you can also see how the CO2 extends laterally over time. So now we get into wave equation-based AVO and the question why we should use the wave equation when we do AVO inversion. In this presentation, I would like to address 2 main aspects. The first one is that web AVO, in contrast to linear AVO, exploits the true nonlinear relationship between reservoir properties and seismic data. And while it may sound very mathematical, I'm referring here to properly modeling and using interbed multiples, mode conversions, and transmission effects in the seismic data. So those effects are usually neglected or regarded as noise by linear AVO inversion. And the second aspect is that web AVO directly inverts for elastic parameters in terms of compressibility and shear compliance. Compressibility and shear compliance, they are the inverse of the bulk and shear moduli, and they are very good parameters to characterize the subsurface because they are much more orthogonal and they are very sensitive to the changes in lithology and fluid effects. And that makes them much more suitable for reservoir characterization than, for example, impedances or VP over VS. I would like to give you an example of wave equation-based inversion. So that's a 2D single parameter example, which I created a couple of years ago for my PhD. But I think it's a very nice demonstration of the value that the wave equation can create. And you see here, we have a subsurface model. So it's a homogeneous embedding with a base layer, and there's a temple above. So the temple, that's the logo of the Delphi consortium. That's where I graduated in Delft. And what inversion tries to achieve is you have some seismic data as input, and from this seismic data, you try to reconstruct the subsurface model. So in this case, we had 21 shots shooting into 21 receivers. So the very first step of the inversion, it's a linear inversion. So you see here, we have a homogeneous background model. That's all the knowledge that we have in the beginning. And then you apply a linear inversion to your seismic data. And the result that you get is the following. You see that the base has been imaged quite properly. You see that the roof has been imaged quite properly. But still you see quite a couple of side lobes, and also the vertical pillars, they are completely absent. And that is an effect of assuming that you have only primary reflections in your seismic data, which is not the case. So what I can do now is I can use this first estimate of the subsurface, and I can update my seismic wave field at every grid cell in the model that you can see. And I do that by adding a first order scattering term to the seismic wave field. And then we repeat the inversion. After then using the second order scattering, we get the following result. And you see that the base has been improved, the roof gets quite a bit sharper, so the resolution improves, but you also start seeing the vertical pillars slowly coming out. And then we just iterate. I think you get the drift of the whole procedure. We use now this latest estimate of the subsurface. We include another order of scattering in the seismic wave field. We repeat the inversion, and then we get into a flip-flop mode, and we can do that 50 times until we end up with the following. And the model that you see here after updating the wave field 50 times is very close to the true subsurface model that you have seen before. So it's interesting that you can properly image the vertical pillars by accounting for multiple mode conversions and the transmission effects. And you can also see that the elastic properties have been estimated in an absolute sense very precisely. So the red color that you see here is very close to the red color that you have seen in the input model. Before we continue with the Sleipner case study, I would like to position the wave equation-based AVO inversion a bit in an historic context. So using seismic AVO all started with intercept and gradient techniques. And while they are still widely used today, I think it is a rather simplistic data model that this technique is based on. So the assumption is that you only have a single geological interface between two half spaces, and your seismic wave propagation is approximated by a single primary reflection from this interface. So what people did then is they progressed in terms of technology, and they developed proper AVO inversion. So in AVO inversion, you look at a stack of geological interfaces, and then each of these interfaces can create a primary reflection. So you have a number of primary reflections that can interfere over the seismic wavelength. And that is where the terms detuning or tuning were developed. What I present today is web AVO inversion, and that's another step in the evolution of AVO technologies. And we're still dealing with a stack of geological interfaces or units, but now we solve the full elastic wave equation. And that means that not only every interface can create a primary, but you properly account for multiple mode conversions and transmission effects. And in fact, you do that by letting every point in the subsurface communicate with every other point in the subsurface. And if you look at it like this, then I think it's fair to say that web AVO is a natural extension of the historic development of AVO technologies. So here are the well logs that we will use in this case study. They come from the well 15913. What should be said is that those logs were acquired outside the plume, so they've never seen the CO2, but they only see the lithology. And from left to right, you see the density, you see BP, VS, and the computed compressibility and the shear compliance. The only reason what we're going to use those well logs for is to estimate seismic wavelets and to build a background model for the inversion. But we don't force the inversion to match any of those properties at the well location. You see this is the overburden, so the cap rock, in total approximately 700 meters thick. And below you see the Euro-Zero formation. And the Euro-Zero formation is characterized by very high compressibilities because it is very compressible due to the high porosities. But you'll see that within the Euro-Zero formation you get those shale layers, and they are part of the characterization exercise. So the injection happens with a deviated well, which has not been logged, but the injection happens from below, and then the CO2 migrates up and gets hopefully securely stored under the cap rock. So this is the seismic to well type that we performed. As for any other AVO inversion, you need seismic wavelets. So you see on the left we have the broadband synthetics that have been created by Kennett modeling using the well logs that I showed before. In the middle you see the seismic at the well location, and on the right you see the matched synthetics. And the match is quite acceptable. It's not perfect, but that is usually the case when you estimate seismic wavelets. This is the result of the wavelet estimation itself. So you see the wavelets as a function of slowness or in terms of angle, whatever you prefer. You can see that they are rather consistent. They have a positive polarity and they have good frequency content with a maximum frequency around 70 Hertz. I have to remind you here that we are shallow. That helps in maintaining a good frequency content. But if you go to deeper targets, you should not expect to get such a good bandwidth of the seismic data. So that is all we need for the inversion. We have wavelets. We build a background using this single well, and then we can run WebAVO. Here you see a summary of the parameters that we used. The inversion was performed on a 3-meter vertical grid. That is again a result of the good frequency content of the seismic, but also of the aquifer being shallow. So it means the velocities are rather low, and that helps in the resolution that you can achieve. The maximum available angle that we found in the seismic was around 32 degrees. And the inversion was performed on a lateral grid of 25 by 25 square meters. So while the inversion is performed per CMP, we repeat the exercise for many CMP locations. And in this way, we can build up a 3D subsurface model. So that is, again, very similar to all the other existing AVO technologies. And in this case, we did 5 total field updates, and that is when the scheme converged. Convergence is reached in our case when neither the subsurface models nor the seismic wave field within the subsurface model does change anymore. I'll show you straight here the inversion result at the well location. So that's again well 15,913. Let me remind you that we are outside of the CO2 plume. So this is only lithology that we see here. You can see that the input seismic has been matched quite nicely. On the very right, you see the residual blown up by a factor of 2. So the match is very good. And on the left, you see the inverted compressibility. The logs, they are shown in red. The inverted compressibility is shown in blue. And the dashed black line, that is the background model. So that's a 4 Hertz low frequency representation of the measured logs. And you can see again, the comparison is not 1-to-1, which is to be expected, but overall we get a quite good comparison. You see the top of the storage formation, you can see the shale break below, you see some variations within the storage formation, and you can also see the base of the layer. So now we move to the center of the plume. Inside the plume, there are no well log data available, but just for reference, I still plot the red curve in the left panel. You can see the background model in the dashed black line, and you can see the inversion result is the blue line. If you look at the seismic data, it has been matched quite nicely again by the synthetics. On the very right, the residual increased a bit, but realizing the increase in the seismic amplitudes, that is very much acceptable. And now if you look at the inverted compressibility, then you can count up to 6 layers that are apparently CO2 filled after the injection. And it's interesting to see that the compressibility went up by a factor of 4 or even 5. And that is a result of the combination of having very high porosities with the low density injected CO2. So the density of the CO2 is approximately 600 kilogram per cubic meter. You may have another layer that is CO2 filled in the shallow part, but it's just below the seismic resolution. But what should be realized here is that the compressibilities for the different layers, they are variable. And we will use these different compressibility readings later on to translate them into different saturations. And that is exactly what we need to come up with a quantitative estimate of the amount of CO2 that we expect to be present in the subsurface. Okay, in the introduction I promised that apart from the elastic properties, WebAVO also solves for the seismic wave field at every grid cell in the inversion domain. And the good point is that we can use this predicted seismic wave field for additional interpretation. So we move outside the plume again. So we go back to the well location outside the plume. And I plot here this wave field, this internal wave field, for the highest angle. We usually plot the wave field in what we call a VVSP display. VVSP stands for virtual VSP display. And you should realize that the time is on the vertical axis and the depth is on the horizontal axis. On the very top, you see again the inverted compressibility. So you can see here the overburden, the top of the storage formation, the shale break below, the variations in the storage formation, and the base. And because the scheme is fully elastic, we can also decompose the internal field into a P component and an S component. So the P data is on the left and the S data is on the right. So let's start by assuming that we have primary reflections only in our data. So that is what conventional AVO inversion would do for you. Then this is a ray path that would fall within your data model. So you have a P source on the top left. You create a downward propagating P event. So everything that dips to the right is propagating down, and everything that dips to the left is propagating up. And then you see that at the bottom of the formation, you create then this primary. And the primary is then measured at the receiver locations again. So why should you care about the wave equation? Because that seems to work so far. I would like to draw your attention to the two events in the bottom right corner of the panel. And I draw some ray path now. And you may see it happening, but the events on the bottom right, they do not have a start. So first of all, they just appear out of the blue. There's no geological interface that can have created them. And time-wise, they fall outside of the inversion window. So what you have to do is you have to have a full elastic data model to properly explain them. And the ray path indicates what happens. You have a P source, you get a downward propagating P event. At the top of the storage formation, you get a conversion from P to S. So now we have to move from the left panel to the right panel. The resulting S wave is still propagating down because it's dipping to the right. And that also tells us that the conversion happened in terms of transmission. And then somewhere within the formation, you get a conversion from S to P. So we move from the right panel to the left panel. And this is the result of inversion of real seismic field data, which makes it of special interest because it demonstrates, on one hand, that those effects are present in seismic data, but it also should be a motivation that they can be properly handled, and that is exactly what wave equation-based AVO inversion does for you. So now we move on inside the plume again. You see this is the location inside the plume. You see the inverted compressibility on top again. You see these very high compressibilities. That is where the CO2 is stored. And inside the plume, it is not so much about mode conversions, but it's more about the conventional multiples as we all know them. So I draw two lines here. So this is the top and the base of the storage formation, or at least where the CO2 is stored. And you can see here that once the energy gets into the plume, it bounces up and down multiple times. And again, you create a very complex wave field. The good thing about WebAVO is that it is not a model-based approach. So you don't have to tell WebAVO if you want to deal with multiples or mode conversions, but it automatically figures that out and interprets this information in the seismic data. So the bottom right corner here, that's always a good QC area, because if there were no multiples and mode conversions in the seismic data, there should be only a very single downward propagating event, and that's your incident field. But as soon as you see downward propagating energy in the bottom right corner, you can be sure that multiples and mode conversions are in your seismic data, and you should start thinking what you can do about it and if you want to do something about it. So we're getting to the end. I show you three figures now. On the very left, you see the background model. This is the starting model along an inline and a cross line. This background model has been built based on the seismic amplitudes. So the seismic amplitudes are so strong that they can really help in building the starting model. In the middle, you see the inverted compressibility, and you see the individual layers, but you also see that within the individual layers, you get different colors. So these are different compressibilities or different saturations. And on the very right, you see a geobody that has been extracted based on the inversion result. So this geobody is directly in depth, which is a unique aspect of wave equation-based inversion, because input to WebAVO is seismic data and time, but output are the reservoir properties directly in depth. And that is very helpful because we want to come up with a quantitative estimate, and we can do this interpretation directly in the depth domain. In terms of resolution, I think the thinnest layers that you may see here, or the thinnest units, they are around 7 to 10 meters, and that is in line with the sampling and the frequency content of the seismic data. The thing what we are missing now is still a relationship between the compressibility and the CO2 saturation. And here we use Gassman modeling or the Gassman equations. We have average properties in terms of porosity and the CO2 density. So the average porosity that we could find in the literature is 36%. The average CO2 density is around 600 kilogram per cubic meter. And using this information, we can then build this curve that you see. And the curve can then be used as a lookup table to convert every compressibility grid cell in the geobody into a CO2 saturation grid cell. And then at the very end, it becomes very simple. You just sum up all those grid cells within the geobody. We know the lateral sampling is 25 by 25 meters. We know the depth sampling is 3 meters, so we know the volume of each grid cell. We multiply each grid cell in the geobody by an average porosity times an average density times a variable compressibility that we got from the inversion. And if you sum this all up, then you get an estimate of 12.1 megatons. So based on the seismic data from 2008, we expect that 12.1 megatons of CO2 are present at this point in time. Now, it turns out, and that brings me to the conclusions, that the estimated amount of 12 megatons is in good agreement with the approximately 11 megatons that were reported to be injected by the time of 2008. I hope that I could demonstrate that multiple scattering within the plume really requires a wave equation-based method to handle the seismic amplitudes correctly. A next step that you could think of would be to apply wave equation-based AVO in a time-lapse mode. And although we haven't done that yet, we are currently using WebAVO in a time-lapse mode. And the described workflow has the potential to also improve hydrocarbon reserve estimates. And that is, of course, where a lot of value is. Because if you can estimate at an early stage with a good accuracy how much hydrocarbons you expect in the subsurface, that would have a big impact on the way you write and implement your field development plans. I'd like to acknowledge the license holders of the PL 046 license, Equinor, Lotos, ExxonMobil, and Total, for making the data available, but also for their permission to publish this work. If you like this presentation, please visit the EAGE YouTube channel to see more webinars.